A warm welcome to the Evolution Show. I'm Johan Landgren. I hope you're great. Next year, the world's first 30-seater hybrid-electric airplane will start test flights in the United States. A plane developed by Heart Aerospace, a Swedish pioneer in the electric plane space. Today, the CEO and founder, Anders Forslund, joins me for an inspiring conversation where we cover everything from new design developments to the first test flights next year, and much more. You definitely don't want to miss this episode. Heart Aerospace is a really exciting private company that I had the opportunity to invest in a few years back and follow closely. Check out the chapters under the video to jump straight to a specific section. I hope you liked the episode, and don't forget, a thumbs up, and consider subscribing to support the show. Okay, let's get going. This is the Evolution Show. Welcome back to the Evolution Show, Anders Forslund.
Thank you, great to be here.
I think it was about 1.5 years ago you were on the show last time, actually, so time flies. And I'm really glad to have you back. I think we have a lot of exciting things to cover. But for those unfamiliar with what you do, you are the founder and CEO of Heart Aerospace, a pioneering Swedish company that is developing a unique 30-seat hybrid electric plane called Heart ES30. And you will start a test flight next year, 2025, in the United States. And the plan is to have it commercially ready by 2028. So perhaps we could start with the plane. Could you tell us briefly about it and explain perhaps something about the different flying modes and range?
Yes, so first of all, Heart, we're operating from a mission of decarbonizing and democratizing air travel. And we believe that the exciting thing about electrification, which I think is a recurring theme on your show, is that it is something that is not only emissions free, but in many cases can be commercially superior. Essentially, reducing, going from internal combustion engines or jet engines to electric motors, you reduce part counts, you reduce mechanical complexity, all of these things that both drive, lower acquisition costs, it drives lower maintenance, and that obviously becomes very exciting. So when we talk about the decarbonization and democratization of air travel, the decarbonization is fairly self-evident, but the democratization is about building an aircraft, a 30-seater aircraft that can operate with really fundamentally different unit economics. So what we set out to do with this is to create an aircraft that meets that value proposition. Today, there are not many 30-seaters flying around. There's one big exception, which is Norway, where sort of 30-seater aircraft creates this fast, flexible way of getting around the country. It's the sort of backbone of the infrastructure where they fly point to point between small communities. And this used to be the case also in the United States. There used to be these small aircraft turboprops connecting airports across America, but they've been since gone out of service. And a large part of that is that the unit economics of jet engines don't really add up for small planes flying short routes. So what we wanted to do is to bring that massive value proposition of electrification to this aerospace industry. The thing that I think we've been working on, to go back to your question, for the past 1.5 years is to figure out a way how to meet that value proposition also when we're with the introduction of a hybrid system. So essentially the electric planes or flying on batteries is great. You meet the zero emissions, you meet the value proposition, but the problem is that about 1 in every 1,000 flights here in the US gets diverted. Essentially, you have an incident on the airport where you're coming into, you have to fly over to a different airport. So that for that you need about 45 minutes of reserve fuel, and you need about on top of that you need 100 nautical miles, which is 185 kilometers of reserves. So that if you want to carry that with batteries, that's a long that's a lot of reserves. Essentially, you're maybe doing a half an hour flight and you're carrying 45 minutes and plus 185 kilometers. So it becomes really cannibalizing on the electric performance of the aircraft. But it's needed, right? Because obviously this happens once in every 1,000 flights, and the sort of safety criteria for aircraft is you want to have a safety record of less than one major incident in 1 billion flight hours. So either you improve air traffic management by a factor 1 million, or you create a provision to deal with these reserve rules. So that's where a hybrid system comes in. So the trick, what you wanted to achieve, or the objective that you want to achieve is to build a hybrid system that is not a large driver of development time. It's not a large driver of the COGS, the cost of the aircraft. Essentially, you don't want the whole economics of the aircraft to be defined by that 1 in 1,000 occurrence. So we worked long and hard on that. We've looked at various different architectures, and what we've landed on now is what we call the independent hybrid system. That means essentially that you're building 2 aircraft in one. You're building a turboprop aircraft and you're building an electric aircraft, and they're operating on the same wing. So you have 4 propellers. The inner 2 propellers are all electric. They're larger diameter, and they're operating at a higher voltage, or not higher voltage, higher power. And they fly all electrically, and the plane is able to fly with those inner nacelles for the sort of 125 mile, 200 kilometers, all electric proposition. So these routes, and then you turn on the outer nacelle, you have a smaller turboprop engine, essentially the form factor of some of the most common small aircraft turboprop engines in the world that you're not using. And then as you employ those turboprops, you can first of all deal with the reserve rules, so you turn them on if there's any incident, or you could use them to fly longer flights, up to 500-mile flights. This has been a departure from how we originally viewed this, where we were essentially designing a series hybrid system with a range extender in the rear fuselage, operating as a generator. And instead, we've gone to this more direct method.
So, but could the plane, I mean, if it needed to, could it go just with the turboprops, or and separately just with the electric motors if it had to?
With the electric motor, yes. With the turboprops, we're still doing the trades there. It certainly can do many phases of the flight. It's a takeoff that we're the all turboprop takeoff. That is the thing that I think is a little bit challenging, especially with the low run or short runway requirements that we're operating.
I was more thinking about landing the plane.
Yeah, landing, of course. Yeah,
I mean, starting is
landing. You don't need a lot of power, but what you do need to do is you need to think about, an aircraft design. I think not many people truly appreciate that. It's very much driven by the corner cases, which means that when you're sizing, when you're deciding how large of a turboprop do I need, how large of an electric motor do I need, it's really about how, what happens if one fails? What happens if one battery fails and we have to shut down that power? There's all of these sort of failure modes that you have to account for. So for instance, if you have a traditional twin aircraft, which operates with 2 jet engines or 2 turboprops, you size the entire aircraft to be able to fly with only one of them, and really size that for losing one of them in the most critical takeoff scenario. So this is where it becomes really interesting. When you're operating with these dual turboprops and electric motors, some of these sizing constraints become a little bit alleviated, which means that we can run with quite small turboprops in this. That's essential because then we can use turboprops of a form factor that are ubiquitous in the sort of larger or smaller commuter segment, and that means that bringing that sort of, which is more used for like 10-seater aircraft up into the 30-seater aircraft proposition becomes very much of an economic benefit. And if you add on top of that these turboprops will be very used very limited in a very limited way, you get a very good maintenance of those as well.
And recently, a really interesting thing, you announced that you're going to develop the prototype and test fly it in the US. And you're also developing a technical team in Los Angeles or in California. So could you tell us a little bit behind, the thinking behind the decision to make the test flights in the US?
What's been exciting about our journey with Heart is that we started this journey as sort of creating the product that meets the demand is in the Nordics. But right now, this aircraft has had, there's a demand for this aircraft in all corners of the world. So we realized that quite early, and we realized that in order to actually deliver on these aircraft to some of our anchor customers that include United Airlines, Air Canada, etc., we need to have a presence in North America, essentially because electric aircraft, you don't want to be flying them across the Atlantic to deliver them. So we always thought about how do we build that presence, both in Europe and the United States, and ultimately in other continents as well. And what we sort of, how we've been reasoning, especially after closing our last financing round, is that when you go into the flight test of this aircraft, then the US is a really good place to do this type of what we call experimental flight tests. It's not when you're doing the conforming flight test with the authorities, it's when you're essentially experimenting, testing, validating your propulsion system. The US has really strong infrastructure for this, and for one of many things is that the weather is much better than it is here in Sweden, which sort of is actually very important. So sort of starting with the sort of milestones that we're hitting now, when we're coming into that flight test of this aircraft, we decided to really start building the team here, and then preparing us for going into that phase. What this also allows us to do is to tap into, well, I think one of the most interesting markets for talent in the world, which is the sort of the LA ecosystem around aerospace. And we've already made our first hire here to start building that team. And
another part of it is, of course, really interesting as well, that you're going to test fly the prototype from the beginning, I understand it, without even a test pilot on board. So, and that's very much thanks to the area you are in California. There's not so many civilians around. So this, I think, can you tell us about the location maybe?
We're building this aircraft, what's called as an optionally piloted system. It's not something that we're going to be certifying this aircraft to do. That is that when you bring this to market, it's going to be operating with 2 pilots. But essentially, when you have the chance that you really don't have a lot to design a clean sheet Part 25 aircraft, you can design the architecture so that it's essentially controllable remotely. And so some of these test flights we're going to be doing remotely, essentially operating them like a large drone. But it's always going to have that sort of bidirectionally optionality. And one of the great things about doing that is that we can be sort of in the there's plenty of airfields out here that essentially, if you remove the pilot from the equation, you just have to be aware of the safety of those on the ground. And if you're in a very remote location, such as desert type airports, that becomes very, very much more viable.
And you can also, I understand, shorten the time frame of the testing, so you don't have to, thanks to, if you can achieve, testing without a pilot, it becomes safer. The marginal for safety, it doesn't have to be so extreme high when you're testing it without a pilot. We're talking about, what do you call it, half a decimal or something in difference, but it makes all the difference.
Yeah, I think that this is really where we're I think the broad, maybe if you know, can elevate it a little bit, like the broader vision here, I think is that, like, look at driverless cars, right? It's the what's been driving that development. You know, it's fairly easy for people to build a driverless car, you know, have a sort of running through like a circuit or, you know, a fenced off place and showing that it worked. And it was very difficult to get it into the real life operation, because every time you're sort of adding a decimal of reliability, it's becomes so much more work. So what I think is really exciting, what we've seen a lot of these, for instance, the eVTOL players are doing, the people that are building flying cars, is that they start by flying autonomously and this, or remotely, and then this sort of, if you do that in a shorter circuit, you could get to that a much earlier phase than when if you were to be flying remotely or autonomously commercially. So I think that's going to be a really important thing. So just some numbers, like you have for commercial aircraft, you have a safety record of 10 to the power minus 9, which means that less than one incident in a billion flight hours, or one you know, catastrophic incident in a billion flight hours. For flight tests, you relax that by a factor 1,000, so you're at 1 in a million instead, which is still pretty safe. But if you do remote testing or any other type of testing that does not involve a human in the loop, you can obviously relax that to, you know, 99%. You can practice destructive testing. I mean, one way of looking at it is sort of almost the way that that SpaceX has done it with their rockets, where they're essentially having very low reliability on success, and they're able to iterate very, very fast. Now, so that's sort of a little bit how we're looking at it as a North Star, saying that, you know, what if we remove some of this, that capability? What could we do? Obviously, you could also do much more extensive testing. Pilots need to go to the bathroom, they need to sleep, they need to eat. There's, like, if you could automate a lot of that testing, you can go very far. I think obviously when you do that, you don't want to be spending all your resources developing and certifying an autonomous systems for it. So that's why we're sort of going for this optionally piloted approach, where we can sort of fork this off in different ways as we progress.
And you know, talking about time frames and so on, can you take us through the plan from the first test flights? Understand starting first half of 2025, and then perhaps to the most important steps in order to reach commercial certification in 2028. What if you could say some of the steps you need to go through?
Yeah, I mean, I can start by elevating a little bit. So my the thing that we really want to change with Heart, that I think that we identified early on, was that we were thinking not just about, like, how does an aircraft look in the 21st century, but how does an aerospace company operate in the 21st century. And if you want to look at a little bit what's the state of the art today of aircraft development, it's been described with this sort of V model diagram, and it's just going to be a little bit technical, but essentially you go through these gates of development where you say, I'm going to do a conceptual design, I'm then going to do a preliminary design, I'm going to do detailed design, I'm going to do that with the few suppliers. They're going to go in, build their components, then you're going to get them, you're going to assemble them, and then you're going to go flight test. And then you're going to certify. Essentially, well, all of these things happening a little bit overlapping, but essentially what that means is that you get one iteration of development. And the problem with that is that works if you're only doing an incremental change to your last development. So if you're building a new version of an established airframe, and you're doing sort of mild improvements on that, then that one iteration is going to be great. Heart is trying not to build an aircraft with too much new stuff, too much innovation, but as you're building a hybrid system for the first time in this, it going through that process of defining the architecture, defining the detailed design, building it all out, then designing the components, and then working all the way up into a certified aircraft and getting that completely right on the first time, it becomes very, very time consuming. And it takes a very long time until you actually have hardware. And that means that you're creating a suboptimal product essentially the product is not going to be as good as it could be. And there's really no reason why to do it that way. I think the reason that people have done it that way is that they feel that it's been too prohibitively expensive to test early. But actually testing early, probably the thing that could save you a lot of money. So if you look at it maybe from an analogy, I would say that think about software development. If a software development worked like you were creating this complex piece of software, you had a bunch of different companies working on a software program, and everything was defined, in a Word document, that everybody wrote the requirements for the software in the Word document. And then you started, collaborating, writing interface control documents, then starting writing the code, but not ever compiling the code. And then sort of, instead you'd create cross-functional groups that would be looking through the code and making sure that it will run. And then you've done it all, and you worked for several years, and then you press the compile button and the software works. I mean, that's a little bit how aerospace company works. There's nobody in the software industry that works that way, right? There's nobody that what you do with the software is you sort of set up your environment, you do your minimum viable product, you actually do like a hello world, making sure that it sort of is working, and then you're compiling, and you're continuously compiling, debugging, changing, and obviously that's very easy to do for a software product, because the cost of pressing that compile button is zero. When you're in aerospace, obviously the cost of testing is not zero. It can be quite substantial, but it's not. But in the grand scheme of things, with the technology development that we've seen, for instance, both in digital testing, which we were using extensively, but also in the field of rapid prototyping, everything from 3D printing components, ubiquitous CNCing, so sort of creating components, to electronics and everything that is the modularization, the software basis of electronics, the ease in which to build composite parts as one-offs. I mean, if you start actually building your process reflecting that new reality that we are in, you can get the price of pressing that compile button is not that high. So that's what we're trying to do with this, and we've actually been demonstrating since we've started this company with our first propulsion system demonstrated in 2020. The ITF, the Iron Burr that we built for all the system in 2022, and now in 2024, going in and actually rolling out our full-scale demonstrator aircraft, starting with the charging and the taxi in 24, and then getting into flight in 25.
And I think it's good to remember, I mean, when people hear about this airplane, a hybrid electric plane, they're often very excited, but they're also a little bit skeptical when you talked about the range. Because and I think it's understandable, because most people don't know that until the early 90s, you have showed me this map, there were hundreds of routes addressing a similar flying range. In the US, for example, and I think there are similarities in Canada, and I think also in New Zealand, for example. And I think I mean, why did it stop? I mean, the increasing oil prices. I mean, I wrote a book about oil, so I know a lot about oil. And so the oil prices that went up during the whole 90s and the 80s and 2000s. So, and with that, of course, fuel costs. And as you have told me, I mean, I didn't understand it before, but I understand it now, that the maintenance cost of an airplane is incredible. But this could change.
Yeah, I mean, I could give my sort of little version of this, but essentially, range. Obviously, you need to have a useful range, and we're only getting to a place with batteries where we have useful range now, and that's going to improve. because you don't want to have an aircraft that can't do anything. And that's also why you need the hybrid system. But besides that, range is a little bit of red herring. Like whenever you're developing a product, you have several dimensions, characteristics of a product. Some of them are competitive and some of them are, so if you look at everything that's sort of makes up a value proposition of an aircraft, range is only one of those things. And for regional planes, it's range has always been quite small. Like the average route length of these 30-seater when they're flying in the 1990s in the United States was 172 miles, so about 270 kilometers. So it's not really about cost, it's not really about range, it's about cost, right? So the reason they stopped flying these aircraft were not because they didn't fly far enough, it was because they did not make economic sense. So when you're creating this technology of electrification, you cannot compete with the energy density of jet fuel. So why compete in that? Like, why not look at this new technology and say, where this shines is that it has zero emissions, right? Which is important, and not only for climate, but also for our environment, for people living close to airport. It also has low noise and short runway operations. So this means that you can build an aircraft or an air travel experience which is much closer, an airport that is not separated from our communities, but an integrated part of our communities. And then you have a good unit economics, a good value proposition there. So those are the things you're trying to optimize for. You're like, don't try to build a long range aircraft with battery electric. Try to make it really shine there. I mean, I'm sometimes saying, it's kind of like comparing, if you were to build an electric bicycle and you'd compare it to a Harley Davidson, and say, can you get the same range of my electric bicycle as I can out of a motorcycle? Is really not the thing. People buy electric bicycles for completely different reasons. Is that they're much more convenient, much closer. They make much less noise. They're much easier to understand. All of those things. If you do electric planes that way, you can build what we think is the sort of everyday air travel.
Yeah, and I thought interesting, you mentioned costs. I mean, I know that, of course, United Airlines, they have ordered 100 planes, and Mesa Airlines, also another American regional airline, have ordered 100 as well, and Canada 30 as well. So, and they obviously understand this because they know the experience. United, I think you mentioned before, they have experience from the 90s and so on. But could you say anything about, in terms of numbers, what are we talking? If you compare a Heart ES30 plane, a 30-seat airplane with 100% turbine engine power plane, are we, in percentage, are we talking 20, 30% in cost savings? Can you say something about that?
Yeah, I mean, so our target is around the 40% mark. Right. And there's a few reasons for that. One is our vision for the future is a world which looks like Norway today, where you have these 30-seaters flying point to point, connecting communities. And that's being subsidized by roughly that number, the 40%. NASA released a report last year about the 40% mark as well, saying that if you get 40% reduction in cost that electric aircraft could give, then you could then you'd go from this market, sort of a market of decline, into a market of rapid expansion. And we see very clearly that can be achieved with this technology. So, I mean, for reference, the turboprop market. So essentially what happened was in the 1970s, there was the oil crisis. You probably wrote about that in your book. The price of oil went up 2x, and what happened there was people started looking at this new technology, turboprops, which is essentially a turbine driving a propeller. It's a very fuel efficient way of air travel, and there was 4 new actors. There was Embraer out of Brazil with the Brasilia. There was de Havilland with the Dash 8, which then became Bombardier. There was ATR developing the ATR 72 and ATR 42, and there was Saab developing the 340. All of these aircraft sort of came within almost a year of each other. In 1984 and 1985, they started entering into service. sort of a little bit as a response to these increased fuel prices, there was a little bit of lag. So this was mid 80s by the time they hit the market, but it was a tremendous success. And these aircraft combined sold in the thousands. But then obviously there was, the oil prices went down significantly in the 1990s. Regional jets became fashionable and actually, kind of flooded the market a little bit based on some, there's details there as well around how these were being subsidized to get into the market. But when we started actually looking at the maintainability of having jet engines on these small aircraft, that became very, very prohibitive. And so what happened was that we went to larger and larger aircraft to sort of be able to pay for those jet engines. You're sort of splitting the cost over all the passengers. And as a consequence of that, the sort of smaller end of the market got really, essentially disappeared. This was also enabled by the fact that the U.S. had deregulated, started the deregulation process of air travel in 1978. So it's kind of strange because, you tend to have, in this, talking about this, you meet a lot of people that are looking at the way the world looks today and thinks that it's sort of the natural convergence of evolution. But actually the fact that we have this sort of monoculture of air travel today that is really operating only, in that sort of segment that we're used to with the sort of wide body, the narrow bodies and the wide bodies. It's just a consequence of a bunch of random events, right? But where are we now, right? Now we're at a place where the price of oil is up again. But that's only one factor. I mean, there's the factor of the sort of acceptance that people are actually concerned about the climate effects, the policies that are being implemented by governments, legislation, etc. There's also a little bit of return. The pendulum is swinging back a little bit, and recognizing that connectivity, even for small communities, is something that should be supported and championed. So you're seeing almost this mega trend saying that let's get some of this back, right? And then you have this technology of electric motors, which is not, the turboprop was like a delta of maybe 20% in fuel efficiency. Electric motors, batteries, comes in and is zero emissions travel and has obviously a lot better unit economics. So this is going to be, the market is there. It's going to be tremendous, and there's several thousands of aircraft, tens of thousands of aircraft that we're going to be seeing deploying over the next few decades. It's a very exciting thing, and I think that everybody's kind of recognizing this. The only question is like how fast will it go, right? How fast? Because the batteries, unlike the jet engines, and the sort of technology, the paradigm that we've been on today, which has been heavily optimized, and you're sort of getting into the increasingly diminished returns. This is a technology that's only in its infancy, and we're going to be seeing tremendous improvements over the coming decades.
Yeah. And speaking of, we have to mention something about batteries. When people hear about EVs, when they came, I was an early adopter with a Tesla back in 2014. I got so many questions about, the charging time and so on. But you have talked about this in previous talks with me, that it's actually quite fast. You can really charge the batteries on an airplane very similarly, actually even faster than an EV. Can you say something about that?
Yeah, a 30 minutes charge time is what we're targeting.
It's fantastic.
And we're seeing that's, from an infrastructure point of view, charging technology is there. It's really about maintaining the temperature of the batteries. So you need an active cooling system. But with that, you can get to those high levels of charging. And you're not. It's not because you're not going from 0 to 100. You're landing with a double-digit percentage of range left in the aircraft.
Yeah, that's great. And okay, we talked a little bit about U.S. market. We can say something about Europe as well. I mean, in Norway, it's the obvious question, and I know that there's been interest from Norwegian airports for Heart Aerospace 30-seater, and as well as New Zealand. Can you say something about maybe Norway and as well, perhaps a little bit about New Zealand as a market?
Yeah, I mean, I think that there's a few. So they're, first of all, great markets. We started, looking at maps of where they operate turboprops and small seater aircraft. I mean, maybe to elevate a little bit, you could say like this, right? Like I said, there not a lot of people fly 30-seaters today. But there are places where small aircraft are commonplace, and they're generally in places where there's a geography. So, for instance, if there's a lot of mountains, if there's islands, all of these things, where you can't really drive easily, you can't really take a train, that's where you have aircraft operating that are much smaller. You don't really have it in places where there's a road network, where there's a rail network, and there's a lot of so if you start looking at that, where are those places? Obviously, New Zealand is one of those places. 2 islands, connected. A lot of, not a lot of population to support large infrastructure. So air travel becomes the backbone. Very similar in Norway. A lot of fjords, a lot of mountains. Quite small population. You don't want to be building out, these high footprint infrastructures there. If you look at Europe as a whole, I think there's a lot of applications in the UK, the Scottish Isles. There's all of these places where there's mountains, there's islands, there's connectivity. The Alps is a really good example. I think that's where you're seeing a lot of connectivity as well, a lot of air travel, islands in the Mediterranean, etc. You're not maybe seeing it flying from, you don't see many 30-seaters flying like between, I don't know, Frankfurt and Munich, which is sort of has a big autobahn between it. But then if you look further, so Europe probably has the strongest, the US has one of the strongest sort of road networks out there, the interstate system. Europe has obviously strong road network, has strong rail network. We're seeing a lot of companies in the developing, or a lot of countries in the developing world that are opting for air travel. Like that's what's happening in Southeast Asia and India, etc. They're really betting on air travel. Combustion, when you're operating with jet engines, there's significant emissions. But if you remove the operational emissions, the footprint of air travel is the best. I have this number for Sweden. So for every car in Sweden, there's about 200 meters of road. So when you visualize the footprint of a car, I mean, if you close your eyes, you think about the 2 tons of metal and everything that's goes into manufacturing that, and then mining that goes into that, and all of that. But you don't really think about that 200 meters of asphalt, right? Which is quite significant. Right, and you can do the similar exercise for rail, which it's not actually the rail carts; it's the construction of the ground infrastructure. For aircraft, it's essentially a short runway that you need, and then you're operating in the sky. This means that if you just remove the operational emission, it's going to be by far the smallest carbon footprint. It's also going to be, it's also the fastest, right? So, and it's also going to be the most affordable. So I think as the rest of the world is building out its infrastructure, they look to air travel, and that's why it's so important. And that's why I think what we're doing in our mission is so critical, because without electrification, you're going to end up in a place where air travel is the largest sector in the transportation industry in terms of emissions. 25% of the total CO2 emissions by 2050.
Yeah.
In all categories, right? So
yeah. Yeah, and there was just to mention something about Sweden, since it's our home country.
Oh, yeah.
And your HQ, of course, in Gothenburg. I mean, I'm born on an island in the middle of Baltic Sea, Gotland, and I know that actually the distance from the mainland to Gotland I think it could actually be achievable even just going 100% electric, but at least to be combining as a hybrid electric plane, it should be quite, perfect. So, and also to Åland, perhaps, and to...
Yeah, so both Åland and Gotland, which are, we have this MOU with Åland. We're really excited about it. It's from Åland to the main airport in Sweden. It's a 135-kilometer flight. Similar to Gotland, obviously it's a really great place. So we're seeing that. I think those are really winning sort of first movers in Sweden, but also obviously in the north and everywhere. We're in Sweden, we don't have, we're not as mountainous as we are in Norway, but obviously air travel infrastructure is equally important. We don't fly a lot of 30-seaters in Sweden, but when you make the unit economics that 40% better, obviously you can operate with the same unit economics as a 70-seater, and that's why electric aircraft is not going to be only for those places like Norway or New Zealand. It's going to be early adopters, but that's why we see it having this mass adoption across places where there are also road and rail, including the United States.
And it's just a few more questions I thought we could cover. I mean, there's so many things to talk about, but you have a timeline for, I mean, when people hear this, they think about, batteries, they will improve over time, but how fast? So you have a timeline, Heart Aerospace has looked at this, and you're talking about perhaps 300 kilometers going full electric from 200 right now by 2035. And a double from 200 to 400 by the late 2030s. I'm very optimistic. I was hoping even faster, but sometimes you're not realistic, But is that something, I mean, 300, 2035, 400 by the late 2030s, is that something you think it's achievable right now? Is that your kind of
very much
vision?
So. Yeah, I mean, I think it's very conservative, actually, even to suggest that. So I think there's a few things here, right? Like, first of all, it's the ES30, the way we design it has a 30-year service life, and you replace the batteries, you can get an improved range, right? So if you get a better battery, you can get an improved range. It's not even linear. It's better than linear, because obviously the reserves that you're carrying, even you're carrying some battery reserves, you don't have to account for that if you get a battery at double the energy density, you get more than double the range, right? Then there's everything that can be improved on the aircraft level. There's a lot of things that can be improved there as well. So ultimately, where I see in the 2050 timeframe is that all those flights, those trips that are around 1,300 kilometers, those could be addressed all electrically or with the technology that we're developing. Some of it might be hybrid, some of it might be with stopover, but you also have to look at it more from a travel time perspective than only replacing individual routes. I think we can do something about 1/3 of the emissions for aviation, and I think that's pretty significant. The question is about what's happening with batteries. I think we're seeing we're on the doorstep of some new and exciting technologies. I think we've been seeing the sort of silicon anode been driving a lot of the development. We're obviously seeing solid state and new chemistries coming in. From a period of plateauing a little bit a few years ago, I'm very, very optimistic that there's new technologies that are coming that is pushing quite significantly. So it's not just about this sort of getting 3% better every year. It's actually coming with new technologies that have a step function.
I have to ask you another question, because Niklas Dahl was my previous guest. He's managing and heading another Swedish company called Oceanbird, and they are developing the world's largest wing sails for freight ships. And it's quite funny, because if you look at the wings, they have been inspired by the wings of an airplane. So they
yeah.
have, So it's like basically wings standing upwards on the deck of the top deck of upper deck of a freight ship. And I asked him if he had any questions for you since you were coming on the show, and he said that perhaps if you can say something about the biggest challenges you've had so far to develop a hybrid electric plane.
Yeah, I mean, I get, this is a question that I get a lot, and maybe I even answered the same way. I'm trying to make some more color, but I don't like to answer the same question the same way every time. But when I get asked this question, I say it's not one big challenge. It's like 100 challenges at once, and it doesn't matter if you get 99 things right. If you design a perfect aircraft, but your landing gears are not, your landing gear is not arriving on time, then you're not going to. They're not going to get into service, or if there's anything about certification or avionics, it's this large chain of activities, and the weakest chain there is the thing that is determining the sort of overall strength of your product. So that I think is the major challenge. It's about being a little bit sort of that leads you almost to be a bit paranoid. Like, are we thinking about everything, the unknown unknowns? What I think is really important is that as you design a novel product with a novel architecture, that you also are aware of Conway's law, which is the sort of the Conway's law is that you're constrained. Your product is always constrained to be a mirror reflection of your organization, and the way. We've seen this with EVs coming out in the market that legacy automakers are struggling to build a financially viable EV. I mean, they have EVs in the market; they're operating at a loss because they've sort of haven't adapted their organization to it, and they haven't adapted their supply chain. So I think the challenge that we're facing collectively is as aircraft are designed with a large supply chain, all of those things together, is to define an architecture both for the aircraft, but also for our co-development. Is really about creating building the infrastructure or the sort of ecosystem to deliver on this value proposition. I think that's where our head has been at a lot for the past year and a half.
Yeah, I understand you. I mean, it's a lot of the small things together that makes the challenge. I mean, it's not a single big thing, but a lot of them. I'm going to wrap up this. It's super interesting to talk to you, Anders. But finally, if you want to say something about the future, I mean, if you look ahead, maybe until 2035 or something like that. Do you see any particular market, like in Europe, US, or if you want to elaborate something about where do you see this going for your company, and perhaps a little bit broader, if you like, for electric aviation?
Yeah, I mean, I think we're going to be seeing these flying by the end of this decade, and then we're going to see a period of rapid expansion. People trying to catch up, and obviously bringing a lot of connectivity back, and I think it's going to be, I'm really excited about it. I'm thinking about the exciting things happening in the short term. We're less than we're getting very close now to actually flying our demonstrator. So showing to the world, it's not going to be just a vision and a PowerPoint anymore. It's going to be actually seeing this thing fly. That's really exciting, and obviously that's going to be very easy for us to imagine over the next few years, and especially around also going into the next decade, how this is going to be a backbone of our transportation infrastructure. Yeah, I think it's going to be a great statement, and I really look forward to see the plane fly. I think a lot of people will be surprised that actually electric planes and hybrid electric planes have a huge potential. So it's going to be great to hear more about that. But thank you so much, Anders. I hope you have a great time in LA, and all goes well now with the development of the first prototype and all the steps you have until you're flying it and so on.
So thanks again. I look forward to have you back again to hear more what's going on for Heart Aerospace. Lots of things happening next year. So thank you, Anders.
Likewise, Johan. Great to speak to you.
Yeah.
Have a good one.
That was all for today, folks. I would love to hear what you think in the comments below. Where do you see the biggest challenges and opportunities with electric planes of this size? And where would you like to see them fly? Yeah, and before you go, if you liked the episode, don't forget a thumbs up and consider subscribing to support the show. I hope to see you next time.